Okay, so the last problem. I will say that this last problem, frames, you are. Every time I say this, something goes awry with my statement and it ends up being less than true. So I will say that there is a 95% chance you are going to have some kind of frame problem on the final exam. You are going to have some sort of indeterminate frame. It may not. You'll have some sort of symmetric frame, not symmetric. You'll have some sort of, like, there'll be some redundancy. There'll be some simple measure in the frame, something to make it so it doesn't take too long to analyze, and there'll also be some complicated element in the frame, something that doesn't make the calculations longer per se, but it forces you to think about a particular issue. So like in the last, well, and then again I just contradict myself. In the last exam, for example, you had that rotated frame, and that I know that threw a lot of people off. I don't want to go into too much detail on that here because I'm not sure how much the professor is going to talk about that on Friday, if he talks about it at all. There was a trick to it, or not really a trick. There was an easier way to deal with the rotated frame, which involved using transformation coordinates, transformation matrices, whatever you want to call them. It's not really something that we covered in this course particularly, um, and I didn't cover it in the review session because I wasn't expecting it to be on there, but on the exam. But noted we can have rotated frames on the exam, on exams. So this one in particular is probably more complicated than anything you would see on the exam itself, which makes it very good practice, right? If you're confident and you're able to do a problem like this without any issues, then you can honestly, I would honestly expect you to be able to solve really any problem, since this one is just so much more complicated than anything else you would probably see. Now, I say complicated with like a certain grain of salt there. It is not. It's not really complicated as much as it is just long, right? You have a lot of work that you have to do for this one, and you'll see that as you as you get started here. So again, I'm not gonna like this. I'm gonna try and keep this one a little bit shorter than the other two, because I don't want to go into too much detail for this. I I strongly encourage you to remove one of the horizontal reactions here. I think that's easiest to work with. You can really move any one. You can remove ax, ay, dx, dy. It doesn't matter which one you choose. I think most people, because this is kind of similar to your pre-lab, not similar, like this frame setup is relatively similar to your pre-lab, I would just go ahead and remove dx. That way our results are a little bit consistent. And if you do that, you'll be left with this system here. Now I'm not going to draw. Well, I'll draw. See, I don't want to give you the moment diagrams here because I think giving you the moment, the hard part is getting the moment diagrams. And if I give you the moment diagrams and everything else is just busy work pretty much. But at the same time, the parts of this video that I wanted to go over were about the moment diagram. So I'll try to go over those issues without actually explicitly drawing the moment diagrams. So what do I mean by that? Let's say that you happen to have a moment diagram that looked like this. Okay, so let's say that this was our P system. Let's say this is just some example that we've never seen before, where your P system has some shape like this, and let's say for example that your what do we want to use here? Actually, I don't know which one we have. I think it's a triangle. Yeah, I think it's a triangle like this. And let's say that this is our MQ system. I don't have an entry in my P system for this kind of shape, right? There's nothing in here about that. The only thing I have is this parabola. So what I'm going to do is I'm going to say that this shape is equal to this rectangle minus this area here. Right? Now I don't have this parabola, but I do have this parabola, and I do have a rectangle. The only thing I don't have is this type of Q system now, right? For these diagrams, I need to match base and base. This base here, I have a triangular Q diagram, but the base here corresponds to the base of the parabola. I need something where the base pretend my Q system pretend my Q system is drawn this way. Okay? So I need something where the bases don't match up. I don't have that in this column, but I can use the last column. Right? The last column is for any length A and B. Right? So in this case, if I wanted something like this, I would just set B equal to L. And then if I wanted something like this, I would set A equal to L. And this is B equal to L, A equals 0. This is A equal to L, B equals 0. So you can see I can get any triangle I want with this general rule at the very end. And so I'm going to use that principle to get this triangle times this parabola. So one where the two bases don't match up. When I do that, in other words, this one down here is going to be M. Let's see, it's going to be a rectangle times a triangle minus this parabola times a triangle. Right. This one would be equal to 1/2 M1 M3 times L. This one here would be equal to 1/12 M1 M3 3A plus B squared on L. There is a typo here. Hong caught this and brought this to my attention, but this one should not be A squared, it should be B squared. I know this is taken from a textbook. It's highly odd for a textbook to have two errors in a single table, so I don't know quite what they were doing, but just keep that in mind. This is actually B squared, 3A plus B squared on L. I said before that for this particular case, I want B equal to L, A equal to 0. So this goes away. I am left with B squared becomes L, so this whole thing becomes L. I'm left with 1/12 M1 M3 times L. So I'm going to do this rectangle times this triangle minus this parabola times this triangle. I'm going to do this minus this, and that will give me the deflection due to this shape. Okay. Finally, the last part I want to talk about is these shapes assume that you're all on the same side of the axis. If you ever have a scenario where you're on opposite sides of the axis, so for example, let's say, just hypothetically speaking, that you end up with a moment diagram that looks something like this, right? You need to go ahead and split this up. So this is one continuous moment diagram, right? Where it's like positive here and negative here, for example. You need to split your moment diagram up here. Let's say that your Q system was some trapezoid like this. I'm going to do a trapezoid times this parabola plus this parabola times this trapezoid. Now you'll note that there are certain rules here about, like, for example, this parabola. It looks like a pretty idyllic parabola, right? Like it's symmetric on both sides. Our parabola in this case is not necessarily symmetric on both sides. It depends on where the peak is. We don't know where the peak. We don't have any guarantee that it's going to be symmetric. We're kind of violating that rule. This parabola, this is probably the most important. This parabola does not have zero slope anywhere. This small parabola does not have zero slope anywhere. So this is not a true parabola. Technically, we're only allowed to use this formula if we have quote-unquote true parabolas, where your tangent here is equal to 0. But the error due to using these formulas instead of actually computing it is going to be extremely small. We're talking like on the order of like maybe 1 to 2% or something. So go ahead and use these parabola equations, even though there's some restrictions on when you can actually use them. We're going to ignore those restrictions for now. The answers will be slightly off, but we're more concerned that you understand like the general procedure. So as long as you've made a serious attempt, as long as like you have almost all the steps in there, as long as you have the general shapes of your moment diagrams correct, especially, that's like the most important thing for this homework assignment, that you get the correct moment diagrams, not just for the beginning, but for the end as well. It'll be fine if you have some small numerical mistakes. We really want to make sure that you can see that you're breaking these up piece by piece, that you're analyzing these piece by piece, that you know how to use this table, for example, or you know how to use moment area theorems. Those are the things that we're really looking for. So yeah, by serious attempt, I mean like you have to actually like, you can't just write the problem statement. You actually have to do like a serious attempt at getting a solution in order to get full credit. So please don't take what I'm saying to be like, oh, I put my name and I wrote the problem and I drew a free body diagram. That's not enough for full credit. You need to actually do a serious attempt. Yeah, so with this, I'm sorry, I know the videos they always turn a little bit longer than I'd like. But if you have any questions, please let one of us know, and please be prepared to spend quite a bit of time on these homework assignments. They're not, as I said before, they're not complicated in the one sense that you don't really have there's nothing particularly outlandish about what we're doing, but they do take a lot of time to solve. So just be prepared for that. Yeah, with that, let's know if you have any other questions.